Welcome to Chapter 3, Part 1. We are going to look at more chemical basis of life, Part 2. We are going to spend this chapter looking at some organic chemistry. So we'll spend a little bit of time on the basics of organic chemistry, and then we'll move right into the macromolecules of life. So organic chemistry in general is based on carbon-based compounds, but not all carbon-based molecules are considered organic molecules. So carbon-based with hydrogen. So all organic molecules have both carbon and hydrogen in them. But carbon is the backbone. It can form 4 chemical bonds. It can form 4 bonds with 4 different atoms, which would be called a chiral carbon, or it can bond up to a triple bond with another carbon atom itself. Even though the majority of our cells are made out of water, everything else is made out of some kind of carbon-based compound. And because of this really diverse ability to form 4 bonds, it's the only one that can, it makes carbon kind of it was once referred to as the duct tape of life. It can kind of hold everything together. So proteins, carbohydrates, nucleic acids, and lipids, our 4 major macromolecules, are all carbon-based compounds. So in organic chemistry, we are really studying carbon-based molecules. And organic molecules contain both carbon and hydrogen. Sorry for the typo there. And the molecules can be very simple, from CO2 all the way to really complex molecules, such as you might consider a glucose molecule more complex. Carbon is very abundant, and macromolecules, like I said before, are very complex organic molecules that are put together to make up the different cells and compounds and molecules of life. Carbon has 4 electrons in its outer shell. 2 of them are paired, but carbon kind of hops electrons from one energy shell to another, and it allows carbon to be able to make 4 bonds. Those bonds most often are going to be single or double bonds. There are triple carbon bonds, but because of bonding angles, triple bonds are really quite difficult to make. Carbon can form both polar and nonpolar bonds. It does not quite have the same or as extensive an electronegativity as, say, oxygen. So when it is bound to something like oxygen, it may actually cause some polarity. So molecules that have nonpolar bonds are not water soluble. Remember, those are hydrophobic, and those that are polar are water soluble, and so that would be hydrophilic. Here's just the atomic structure of carbon. You can see that it has the 2 energy shells. And there's a look at its orbitals within those energy shells, and you can see that second energy shell only has those 4 electrons, so it really wants 4 more. Here's just an example of a polar type molecule. This is actually an amphipathic molecule. Carbon to hydrogen bonding is fairly equal. So when you have a CH molecule, like a CH3, a methane, that is actually a nonpolar. It's electrically neutral and makes it a nonpolar molecule. Because carbon, remember, does not have the same electronegativity as oxygen. But over on the right side of this amphipathic molecule, carbon is double bound to oxygen and to another oxygen with a hydrogen on it, and this causes a little bit of polarity in those bonds. So the left side of this molecule is nonpolar, whereas the right side of this molecule is polar. And this is just to show you that carbon itself as an atom can form both polar and nonpolar covalent bonds. That brings us to the topic of a functional group. When we start looking at our macromolecules, you're going to notice, particularly amino acids in proteins, we're going to notice that some of these molecules have what's referred to as a functional group. This is a region within the molecule where the atoms are grouped together, and this grouping gives them a very specific chemical feature, and that feature is very important to the molecule's function. So each type of functional group will exhibit the same properties as all of the other molecules in which that occurs. For example, amino acids. Amino acids all have the same functional group. Every amino acid has the same chemical structure with the exception of one. one region of each individual amino acid will differ. So the part of the amino acids that are the same, that are consistently the same from one to the next, is the functional group. And the one region of that molecule that is different is referred to as the R group. So here we have some different types of functional groups. You can see on the left we have an amino, a carbonyl, carboxyl, hydroxyl. These are the different functional groups that are found bound to carbon. So we can have a carbon structure, and you can see in amino acids there's an R group bound to an NH2. And the NH2 is an amine group. So that's referred to as an amino. That's why they're called amino acids. Now, carbon-based molecules, oftentimes, because of that ability of carbon to form 4 different bonds, these molecules can sometimes have different structures and different bond arrangements, and those are referred to as isomers. Now, we have 2 major classes of isomers. We have structural isomers and we have stereoisomers. Structural isomers contain all the same atoms, same number of atoms, but how those atoms are put together is different. So if I gave one of you, or I gave 2 of you, each of you a box of the same Lego bricks, all the same number of all the same colors, you would put them together, but you may put them together differently. That would be a structural isomer. You have all of the same numbers and of each atom in each type of block, you just put them together differently. Now, stereoisomers are the second major class of isomer, and these molecules have the same bonding relationships, but how those bond relationships are spaced, what's referred to as spatial positioning, is going to be different. And because of this, we have 2 different subclasses of isomers called that fall under their forms of stereoisomers, referred to as geometric isomers and enantiomers. So let's take a look at some examples, because isomers are best understood by looking at them. So here I have 2 structural isomers. On the left, I have valine, C5H11NO2. Valine is an essential amino acid. You can see the NH2 up there on the top left. So we've got that, we have that amine group. If we move over to the right, we have C5H11NO2. We have the same chemical formula, but because these atoms are put together in a completely different arrangement, we have a completely different molecule. This is a liquid. Amyl nitrate is a liquid, and it's also used in forming of the drug of some of the street drugs known as poppers or uppers. Now, in stereoisomers, remember we have 2 subclasses. We have the enantiomers and the geometric isomers. Now, enantiomers are 2 molecules that are spatially arranged so that they are mirror images of each other. You cannot superimpose these 2 molecules. So highlighted in yellow there are the 2 regions that are the mirror image of each other. Notice if we just turned those 2 molecules in, we pivoted the one on the left towards the right and the one on the right towards the left, kind of folded them into each other. If we held them face to face, you would see that they are actually mirror images. Think of your thumbs as the hydrogens that are bound to that chiral carbon in the center. Think of your thumb as those hydrogens. Now turn those two hydrogens towards each other so your hands are facing each other. Your hands are enantiomers. You cannot superimpose your left hand on your right hand. You can't. It wouldn't be the same. Otherwise, you would have 2 left hands or 2 right hands. Now, at the bottom there, we have a geometric isomer. And highlighted in blue is where the changes are from one molecule to another. So this is referred to as a 4-carbon stereoisomer, and it's geometric. They are not mirror images of each other so much as we have just kind of some changes or rearrangements of where those hydrogens are. So we have the same basic skeletal system, the same functional group. We're just moving around some of those other, some of them are facing in different spatial arrangements. On your written exam, you are going to have to be able to recognize structural isomers and then the 2 classes of stereoisomers, enantiomers or geometrics. Here's just a few other examples. Here's isopropyl alcohol versus propyl alcohol. We have a complete change in that bonding arrangement. Down in the middle here, we have 2 geometric isomers. So the hydrogen is still bound. This one I like because on the left you can see the carbon, that second carbon in green, the hydrogen is pointing up. In the second molecule, that second carbon in green, the hydrogen is pointing down. It's still bound to the same carbon, just where on that carbon is different. In the top, a structural isomer, it's bound to a completely different carbon. Okay? So in the isopropyl alcohol, that hydroxyl group is bound to the center carbon, whereas in propyl alcohol, it's bound to the terminal carbon at the end. And then you can see in the geometrics, still bound to the same carbon, just facing it's a different spatial arrangement, facing a different direction. And then of course down at the bottom, the enantiomers, those are mirror images of each other. So when you're looking at differences, when you're looking on your exam at differences between these isomers, look and see if it's bound to the same carbon. These are always going to be revolved around carbons. So look to see if that R group or that functional group that you're referring to, that you notice is different, is it bound to a different carbon? If it is, then it's a structural isomer. If it's bound to the same carbon, but it's moving in a different direction or it has a different bond angle, it's a geometric isomer. If I can take those two molecules and fold them onto each other in their mirror images, then I know I have an enantiomer. So that brings us to the four major types of organic molecules and macromolecules. And these four different types of molecules are the carbohydrates, lipids, proteins, and nucleic acids. We're going to cover carbohydrates and lipids now, and then in lecture 2, we're going to cover proteins and nucleic acids. Proteins and nucleic acids are really big groups of macromolecules and require a little bit more time. So we'll cover those in lecture 2. So let's talk about carbohydrates and lipids. Carbohydrates are your sugars, and they are composed of carbon, hydrogen, and oxygen. So when you see CHO in the molecular formula, most of the time you are looking at some type of carbohydrate. You also will often have twice as much hydrogen as carbon and oxygen in the actual molecule itself. So you can see we have CHO, we have C sub N, H2O, and sub N. So it's carbon with some H2O. Most of the carbon atoms in a carbohydrate are going to be linked to some kind of OH or H, right? Some kind of hydroxyl or hydrogen. And carbohydrates come as monosaccharides. That would be a single sugar molecule, such as glucose, galactose, or mannose there. Disaccharides, such as sucrose and fructose, and those are where we have two monosaccharides bound together. And then they come as polysaccharides. And polysaccharides are things like starches and complex sugars, where we have multiple single sugar units all bound together to form very large structures. Now, this monosaccharide is referred to as a monomer. All macromolecules, with the exception of lipids, have what's known as a monomer unit. That single molecule, glucose, is a monomer of polysaccharides. Polysaccharides, take starch for example. Glucose is a carbohydrate. It's a monosaccharide. As a monosaccharide, multiple hundreds of or thousands of glucose molecules can be bound together to create a polysaccharide. And that would make glucose the monomer unit. That glucose as a monosaccharide is the monomer unit of carbohydrates. Galactose is a monomer unit of disaccharides and polysaccharides. So monosaccharides are known as the simplest sugar. They contain usually anywhere from 5 to 6 different carbons. They can be pentoses or deoxyriboses. You can see we have just a bit of a difference between one has one more oxygen than the other. Hexose and glucose are C6H12O6. When you see that ratio of 1 to 2 to 1 carbon to hydrogen to oxygen, you're looking at a sugar. Now, sugars can exist in both linear and ring-like structures. It doesn't make a difference whether it's in linear form or ring form. It's still considered the same sugar as long as those bond arrangements are the same. So you can see here in our example, we have alpha D glucose in both linear form and in its ring form. Glucose is the monosaccharide that's really kind of the most important. We talk about glucose a lot because it's that basic energy molecule that most cells will use for energy, will break down for energy. Glucose does have several structural isomers. Here, glucose and galactose are actually structural isomers of each other. There are enantiomers and stereoisomer forms of glucose as well. Alpha and beta glucose are geometric isomers. We have a hydroxyl group above the ring in alpha glucose and below the ring in beta glucose. And D and L glucose are mirror images of each other. Now, this is important because D glucose we can actually utilize. Our cells can use D glucose as an energy source, but L glucose we cannot. Our enzymes are incapable of breaking down L glucose. This happens with a lot of drugs and things like that, pharmaceuticals as well. In the pharmaceutical industry, those enantiomers or stereoisomers, you want to make sure that a molecule is not an isomer of something, and because oftentimes the isomers will not work. And that has to do with our proteins and how specific they are. So here are just some pictures of our different structures. You can see here's our enantiomers of each other on the right there, the D glucose and L glucose, and on the left there are your ring structures, your alpha and D glucose, and in the top right you can see that beta D galactose. Disaccharides are when we have a sugar that's made up of two monosaccharides bound together. When glucose binds to fructose, we end up with sucrose, which is our simple table sugar. How these are put together, the bond that occurs between two monosaccharides is referred to as a glycosidic bond. Glycosidic, glycosidic bond. These bonds are formed by a reaction called a dehydration or condensation reaction. In a condensation or dehydration reaction, what we're doing is this molecule here we have our glucose molecule, this OH is going to form a water molecule with this hydrogen atom here. So you can see that we lose, this oxygen moves down, we end up with an H2O. Right? We lose one of these oxygens here. We lose this hydrogen here and this hydrogen here. This oxygen, that oxygen is right here. Okay? And these guys come together and we end up with a water molecule on the side. We are dehydrating the two molecules when they come together. So it's referred to as a dehydration. Oftentimes, more often than not, it's called a condensation reaction because we're condensing water out of the two molecules. Now, if we want to break these sugars apart, all we have to do is put that water molecule back in. And if we put that water molecule back in, then we are rehydrating those two molecules, and this would be called, a hydrolysis reaction. A polysaccharide is when we have three or more monosaccharides linked together, and they form these big, long polymer-like molecules, such as starch or glycogen. We store glucose in our cells. We store it in our liver cells in the form of glycogen. Starch is how plants store their energy. Think about potatoes and turnips and root vegetables. Those are very starchy vegetables. And that's because those in its potato form, a potato is like a seed. It's a tuber. And we can put the potato in the dirt. Well, the potato plant is not getting any sun. There's no photosynthesis occurring. So the potato has to store enough energy in order to grow until it reaches branches and stalks, can reach up over kind of penetrate through the surface of the dirt and then start to receive sunlight for photosynthesis to occur. So there has to be enough energy stored, and we have to condense that energy up, and that's how we get these big, long polymer-like molecules. So starch is a form of glucose storage for plants. Glycogen is the same thing. It's a form of glucose storage in our liver for our own cells. If we run out of energy, we start releasing glycogen because we're not taking in any glucose. Or in the fight or flight syndrome, our liver will dump a bunch of glycogen We'll break up glycogen into glucose and dump it into our bloodstream so we get a bunch of sugar for a big burst of energy. There are structural polysaccharides as well. Cellulose is used to make up the cell wall of plants, and it has a very strong structure. Cellulose is also made up of glucose molecules, but the bond angle between those glucose molecules is different. So you can see here, right here in cellulose, we have what's called a 1,4 beta-glycosidic bond. And here in ours, in starches that we can use, and you can see here in glycogen, which we can also use for energy, these are formed with what's known as an alpha 1,6 glycosidic bond. The bond angle is different. And by changing the bond angle, we can thereby change what enzymes can use it. Notice that the bond angle between the two neighboring glucose molecules, here the oxygen is pointing down, and here in cellulose it is pointing up. That makes a difference in how our enzymes in our own cells can break that down. And that is why our cells can break down glycogen and starch for energy. Cellulose, we cannot. Cellulose is fiber for us. It just goes right through our digestive tract. That brings us to lipids. Now, lipids are made mostly of hydrogen and carbon atoms only. Here we have a triglyceride, and there are a couple of different classes of lipids. Also, lipids are the one class of macromolecule that do not have a monomer unit. One of the most defining features of lipids is they are nonpolar, and so that makes them insoluble in water. So these are the fats. Fats are a mix of triglycerides. They're sometimes called triacylglycerides. We have fatty acids bound to a glycerol molecule. They are bound through either a dehydration or condensation reaction, and again, will be broken apart by hydrolysis. Here's just a glycerol molecule showing you we add it to the fatty acid chains. This is where the water molecule is coming from in a condensation reaction. And so the bond is made directly between an oxygen and a carbon, and we have the triglyceride. Fatty acids can come as either a saturated or unsaturated fatty acid. Saturated fatty acids contain all single covalent bonds between the carbon molecules. You can see here that they are very long and linear and compact. Unsaturated carbon bonds means the carbons are not completely saturated by hydrogens. These are all carbons that are saturated by hydrogen molecules. Here, these two carbons are not. They only have one hydrogen bound up here, and carbon wants 4 bonds. So we get a double bond here between carbons. Same thing going on here. And we start to get double bonds between these carbons. It causes that fatty acyl tail, or that hydrocarbon tail, to bend or kink. And these unsaturated fatty acids cannot line up and be real compact. So our saturated fatty acids tend to be solid at room temperature. Animal fats, butter, those sorts of things. Then we have unsaturated fatty acids, and those are usually make up our oils. So olive oil, plant oils, most plant fatty acids are going to be, most plant fats are liquid at room temperature. And it's because they are unsaturated, so they are unable to be as compact, as tightly packed as the animal fats. Fats are very important for energy storage because 1 gram of fat stores twice or more as much energy as a single gram of glycogen or starch. So we can store tons and tons of energy. And when we get into our section on metabolism, we'll look at how fats can be used as a greater source of energy than sugars, but sugars are easier to break down, so they're always going to be used first. Fats are oftentimes also used structurally. We can't survive without fat. The fat is used for insulation and protection. Phospholipids are another class of lipids, glycerol with 2 fatty acid chains instead of 3. So we have the fats, which are your triglycerides, and then we have our phospholipids. And the phosphate group attached to the glycerol is important as well. They are also formed through condensation reactions, broken apart by hydrolysis reactions. But the phospholipids are an amphipathic molecule. They have a phosphate region that is polar and hydrophilic, and a fatty acid chain or hydrocarbon chain that's nonpolar and hydrophobic. And phospholipids are important because they form our cell membranes. So here's our typical phospholipid. Here's the polar head. Here's that phosphate group. And then we have these long nonpolar fatty acid chains. Steroids are our third classification of lipids. They are made up of 4 rings, carbon rings, all interconnected and joined together. They tend to not be very water soluble. Cholesterol is our prime example, and some hormones. Hormones come from usually cholesterol, which is a steroid. So we have estrogen and testosterone, which are structurally incredibly similar. They really only differ in a small amount. So here on the left we have estrogen, and here on the right we have testosterone. And cholesterol is what is converted into these different hormones. Now, nucleic acids. We're going to get into nucleic acids and proteins in our next lecture. So I'm going to end things here, and we will pick up with nucleic acids and proteins for the remainder of chapter 3.